Seeing there's none, John Mitnick, Operations, Engineering, Construction, is going to talk to us about the 10 Mile Creek design. Welcome back, John.
Thank you. All right. So, 10 Mile Creek. There's been obviously a lot of discussion recently about 10 Mile Creek. So what I want to do is quickly brief the committee on what plans that your staff has in place and they're working on right now to go into that facility and take it from its existing condition and the way we're operating it today, storing 1 foot of water, and turn it into a facility that can store 4 feet of water. Just as a quick refresher, this is the facility itself, consists of roughly a 550-acre impoundment located here. 10 Mile Creek runs along the periphery of it, it's I-95 and the Turnpike. In conjunction with the reservoir or impoundment itself, there's about a 123-acre STA located right here. So water will enter the facility through a main pump station coming off of 10 Mile Creek, flow into the impounded area, and then there's a second pump station that will move that water over into the STA prior to it being discharged back into 10 Mile Creek downstream of the Gordy Road structure. The original design of the facility was constructed to store about 11 feet of water, or 6,000 acre feet, and capture that excess stormwater prior to it being discharged over the Gordy Road structure, pull it into the impoundment or the reservoir, and then subsequently treat it through the stormwater treatment area. I'm not going to go back and run through the entire history of the project and how we got to where we are today, but the 3 main items that we're looking at remediating from that experience are, 1, the collector ditch that runs on the interior portion of the facility, just inside the interior toe of the embankment. 2, there are some voids underneath that soil cement apron. The facility has not been in use for about 10 years. Over this 10-year period, there's been rainwater that's run down the soil cement and has eroded the toe. And there's some voids underneath that soil cement apron at the bottom of the toe. So we're going to go in and fix that, as well as there were some wildlife entrapment issues associated with the stair steps that are located at the top of the facility here. So we'll go in and cut down those stair steps and level them off. Specifically, when I'm talking about the collector ditch on the interior portions, what we're looking at doing is scraping down some of the interior, this green shaded area, and using that material to fill in this collector ditch that just runs down the inside of the reservoir, or the inside of the impoundment. On this graphic here, you can see it's shaded in 2 different colors, yellow and purple. There's different methodologies and different approaches within those 2 reaches. Within the reach that is shaded yellow, we'll fill in the collector ditch and also incorporate a soil bentonite clay layer to reconnect the clay layer that is already present in those locations, whereas the difference in the reach that is shaded in purple, it does not have that feature associated with it, so we'll just be filling in the collector ditch with backfill. So what does all that look like from a cross-sectional view and looking across the embankment? What you're looking at here is, this is the embankment, the existing collector ditch, and the interior portion of the impoundment here. So we'll be taking this material out of the interior portion, filling in the collector ditch, which is up to this red shaded area, again reestablishing a 2-foot thick soil bentonite clay layer so as to seal off that collector ditch and reestablish that impermeable layer that runs across that portion of the site here in yellow. As we come up the embankment, cutting down those stair steps up here at the top of it. In addition, to address some of the erosion that was happening at the toe of the embankment, we'll be adding some, increasing the number of plantings or vegetation there at the toe. It's a technique that we've used in other facilities. We've used it in canals. We use it in the STAs for windbreak, so as to not have wave-generated waves running up on the levees itself. So we'll be incorporating that feature into this design as well. So generally speaking, why are we doing all of this? And it is really all about seepage. Whether it's an embankment, a levee, a berm, any earthen structure that holds back water higher on one side than it does on the other is going to seep. You're going to have water moving through it. Water wants to move through the path of least resistance and get to its lower elevation. When you build an impoundment, the critical part of that is how you control that seepage, how you manage that seepage. You want that seepage to move through, and you want it to come out clean and clear on the other side, and you don't want it to come out in excessive velocities such that it's starting to transport material with it. When it does do that, then that leads to erosion and internal piping within the embankment, which causes levees and dams to fail. So it's all about how you control that seepage. So what you're looking at here are some model runs. Both on the top is without the collector ditch filled in, and the bottom is with the collector ditch filled in. And what you want to pay attention to, in addition, it's probably really hard to see, but other than these faint green lines, what you're paying attention to is this dashed blue line. That's what we call the phreatic surface, and that's the model prediction of how seepage is going to move through that embankment. So you're looking at over here where it exits into 10 Mile Creek, that it is, like I said, not the velocities within our guidelines, within factors of safety, as well as that seepage is not exiting, or what we call daylighting, that embankment too high above the water line of whatever the normal water is of the creek itself. When it does that, then you'll have sloughing off the canal banks and erosion, and you'll start eating into the canal banks. So in comparing the top graphic to the bottom graphic, you can see up here that blue line stays pretty high. That's because as water comes in through the collector ditch, bypasses this impermeable layer here, and maintains a higher elevation coming right underneath it and starts popping up sooner over here. So on the bottom, with the collector ditch filled in and you've reestablished that connection or that cutoff, you can see how it drops down and is exiting much lower down into the canal, into the creek bank. So that's what you're looking for and how you control that seepage. As far as where we are right now, we're just finishing up the design. We're looking to move to construction, and with those remediation features in November of this year. And one of the reasons for that is we want to construct all of that work in the dry season, during the dry season. So it's like some of our other projects, we have sequenced it where you can't do some work in the wet season, but you have to do it all in the dry season. This is one of those projects that lends itself to that, and you want to have all that construction activity during the dry season. So with that, be happy to answer any questions.
Thank you, John. Any questions? Yes, Jim.
Thank you, John. On the issue of seepage management, was that seepage canal you were showing us, was that built as part of the project, or is that a local 298 ditch?
Let me back up. So on this side of the facility, it's 10 Mile Creek. In the model graphic that I showed you, that exterior canal wasn't a seepage ditch, it was 10 Mile Creek itself. On other portions of the perimeter of the facility, they are canals that are part of North St. Lucie's Water Control District system.
Which were not designed as seepage canals.
Correct.
Do you anticipate you'd have problems with that long term?
Problems with the seepage moving into those canals, or problems with their canals?
With erosions in the canals caused by the seepage.
Okay. Right now, as it sits today, their canals are configured and constructed on a one-to-one slope, so very steep side slopes on their canal system. Based on what we've done so far and looking at that, the amount of seepage and the velocities that we have moving in that direction towards some of their canals does not impact or does not change their existing condition. They have a slope stability issue today. Regardless of whether or not 10 Mile Creek is there, they have a slope stability issue with their canal system the way it is currently constructed. That is something for that operation and maintenance entity that needs to take care of and address.
So if as we take over and operate 10 Mile Creek, you have seepage, you have erosion problems in those canals or those ditches that are controlled by the local district, do we have access to them to do erosion repair?
No,
And are they constructed so that we can get equipment in there to do that?
They are outside of our project boundaries and outside of our property.
So what happens if there's erosion in those canals due to the seepage from our project?
Again, the water that moves off of our project is not changing their condition. They have their slope stability issues as it stands today. To the extent that you would have sloughing and erosion of that canal bank, and it would begin to affect or impinge upon our property and our project, then we would have to address it.
We'll talk more tomorrow.
Yes, sir.
Just to follow up on that, I mean, what I think I hear you saying is that it doesn't exacerbate base condition. Is that an accurate
Yes, sir.
statement? So, I mean, would we be able to confidently show that we don't contribute additionally to their sloughing condition, their erosion condition?
We do not change their existing condition, yes. They have a slope stability problem today.
Okay. My second question was, you had the $7 million remediation cost, and I just want to be sure that I'm clear. That's project cost, or is that remediation cost, and then there's project cost on top of it to be operational?
That does not include the long-term operating costs.
No, I understand, but so at the end of, because in my mind, remediation is, hey, I take care of the problems so that I can do the project. Is that the way it is, or the remediation also includes getting the project to the point of operation, so then you can flip the switch and operate it? It doesn't include long-term operating costs. So is that the total, what I'll call construction cost of the
Yes.
project? Okay. Yes.
Just a comment, same thing, I'll spend the bulk of my comments tomorrow, but I just want to say that this is a great project. I've spent an awful lot of time on 10 Mile Creek with these guys, and they've really done a great job of drawing on this agency's experience in operating above-ground impoundments. And you look at the 60,000 acres of STAs that we successfully operate, and they've drawn on some of the best and brightest talent and applied it to this project. Moving it into its bright new future is an awesome opportunity for us as a board, consistent with our completing projects, and I'm fully in support. I drove by Gordy Road, the Gordy Road discharge structure last night. That thing is blowing pretty strong right now with basin runoff, and just to think that we could knock a lot of that nutrient load out of that discharge that's going into the North Fork of the St. Lucie River is a pretty incredible opportunity. It'll be online in 2017. Check it off the list, and let's move on to the next one. So thanks for all your work on this.
Any further comments? Any public comment? Richard Bissell, Division of Real Estate Director. We'll get a general update on real estate activity. Welcome, Richard.
Thank you very much. I'm here to give you an update this afternoon on our current and upcoming real estate activity. I'm going to give this to you.